So our experiment for this week is the flame test laboratory, looking at the colours produced by metal ions when you burn them in alcohol. So as we can see here, we can get a nice yellow for a metal like barium, red for a metal like lithium, green for copper, and blue for lead. When you watch fireworks on the 4th of July, the different colours you're getting are because of the different kinds of metal ions being burned up. So the burning of the metal ion causes the excitation of an electron into a higher energy level, a higher shell in the atom. We call this a quantized energy leap. Now the electron will eventually drop back down to its original energy level. That's a quantized jump which takes a specific change in energy. Because that energy drop is specific, the frequency of the radiation to produce that energy is also specific, a specific wavelength of radiation, and so we see a very specific colour produced depending on that energy gap for the electron, which depends on the particular metal being burned. Now in the laboratory, you'll be assigned a specific element, and when you're looking at that element in the laboratory, take a note of the colour its flame produces, and then match that colour to the representative wavelength in the table in the laboratory report. You can then use that wavelength to perform your calculations and work out the energy for a mole of photons for that element. First, convert that wavelength from nanometers into meters by dividing by 1,000,000,000, 10 to the power of 9, to turn it into a wavelength in meters. Next, rearrange Einstein's equation for the speed of light to work out the frequency of that radiation. Remember that the speed of light is 3 times 10 to the power of 8 meters per second. You can then work out the energy of a photon by using that frequency value you've calculated and multiplying it by Planck's constant. Finally, use your value for the energy of a photon and multiply it by Avogadro's number, 6.022 times 10 to the power of 23, to work out the energy for a mole of photons for that particular metal ion.